All right. So, welcome back to this book club meeting. Today we're going to be looking at capacitance, inductance, and then first and second order transient circuits. And so I'd mentioned this in kind of like the beginning of the Zoom session, but for this chapter on first and second order transient circuits, I'm not so much going to present slides, but we're probably just going to walk through examples in the book and talk about things because it does get a little bit more involved and putting together. I didn't have much time to put together slides, honestly, but let's go ahead and get started here. So, capacitance and inductance. Here, just kind of like the learning goals straight from the chapter, right? We're going to be, and so this is chapter 6 in the book. So we're going to be looking at the circuit models for inductors and capacitors, calculating stored energy, um, and then trying to understand these concepts of continuity for the inductor current and for the capacitor voltage, and then um, calculating voltages and currents, for circuits that just have DC sources. So we're going to take a look at, AC sources probably, I think, in chapter 8, but for now, we're kind of just sticking to DC and really looking at transients. Again, that's going to be in chapter 7, which is coming up again. Um, and then finally, just looking at how to combine capacitors and inductors when they're connected in series or in parallel. Um, So, capacitor is a circuit element that consists of two conducting surfaces separated by a dielectric. And I've drawn it out here on the bottom right. So there's, just two plates of conductive material. And, these surfaces have some area A, and they're separated by a distance D, right, which I've kind of drawn out in this figure. And so, the statement here has mentions a dielectric, and that's basically just an insulator that can be used to store electric fields. And so dielectrics have this property called permittivity, and that's measured in farads per meter, where, we define, um, we usually define the permittivity in terms of permittivity of free space. So this is epsilon naught, and this is 8.85 times 10 to the minus 12 farads per meter. And so they chose this constant just because it's the permittivity of air, really, right? So if we have a relative permittivity of one, right? So epsilon sub r, if that's just one, then we're just dealing with a dielectric of air, which is hardly ever the case, really. Um, right? And in the capacitors that you'll find that are actually manufactured, they usually have a really high relative, high permittivity relative to free space. So you'll usually see things like on the order of 1,000 for multi-layer ceramic capacitors. And I think for things like electrolytic capacitors, which are a little bit bigger, maybe in the tens or hundreds. So just something to, keep in mind whenever you see this epsilon naught, it's just a number really. And it's, in terms of farads per meter. So because of this, as you have more relative permittivity, you'll have more capacitance, right? And if these plates are separated further apart, you'll have less capacitance, right? So it's just what a capacitor is really. Um, and so capacitors are able to store energy in the form of an electric field. And so what happens is as you excite, these two plates, the charged particles will start to accumulate on the plates, right? And then they'll kind of stop flowing, um, right? And so as they accumulate onto the plate, right, imagine you might have a bunch of these electrons sitting up here. And so it builds up an electric field, right? Because you have these charges and they're trying to repel each other, right? And so that repulsion force kind of creating this electric field. on the plates there. And so as the charges build up, right, they're going to actually take on whatever voltage is being applied across the capacitor to a certain point where, the current just kind of stops flowing. Right. And so they've defined that the amount of charge is proportional to the voltage across the plates. Right. So this is that Q equals CV. Right. So if there's more voltage, as more charges build up on those plates, the voltage is going up as well. Um, and so from this, right, we have an expression for the charge on a capacitor and how it relates to the voltage. We can actually figure out current, right? Because current by definition is just the change in charge over time. So dq by dt. We had discussed that before. And if we assume that the capacitance doesn't change over time and we just take the derivative, right, of this CV, then we end up with the current through a capacitor is equal to the capacitance times the change in voltage over time. And so from this, you can figure out, the power, which again, by definition, is just the current times voltage always. You find that to be C dV by dt, right, which is the current that we just figured out here times V. And so that's just C dV squared by dt. Um, and from that, you can figure out the energy, right? An expression for the energy. Energy in general is just the integral of power. And so that's given by half CV squared. Um, right, if you take the integral of this expression here. And so, in circuits, the symbol for a capacitor is just these two parallel plates. Pretty straightforward there. And I think a lot of that might be somewhat review from 151 a little bit, right? So we haven't really hit anything too complicated yet, I think. So here's one thing that might have been glossed over, in 151, I think, a little bit, but capacitor voltage can't change instantaneously. And we had looked a lot at, the capacitor charging circuit in the past, where you have just a resistor and a capacitor, and you suddenly excite it with some, DC voltage source, and we watched what happened to the capacitor voltage over time, right? If you look at that plot over time, you see that it's exponentially increasing, right? If we close this at time zero, and that's a resistor there. So this capacitor voltage, right, can't change instantaneously. And this actually comes directly from those expressions that we had just found. So we found that the current through a capacitor is given by C dV by dt. All right, and if we solve this for dV by dt, we find that that's equal to I divided by C. And this kind of implies that the voltage must be differentiable in the first place, right? If the voltage isn't differentiable, then this dV by dt doesn't have a solution. So this means that there aren't any jump discontinuities, which just means that the voltage can't change instantaneously. So that's one important takeaway that you should kind of have in the back of your mind, right? This capacitor voltage can't change instantaneously, and so that's kind of one of the learning goals of this chapter is kind of to understand, these concepts of continuity. And right, so the calculus that we learn is not completely useless. It does come into play here. All right, so capacitors behave like an open at DC. And so the electric field, right, is trying to keep that voltage constant. Um, and then again, going back to the equations that we had here, since I is given by, right, the current's given by C dV by dt. When this dV by dt is zero, right, and that's kind of what happens at DC, right, the voltage is no longer changing, then we have that the current is just equal to zero, right? I is equal to C times zero. That's just going to be zero. Um, and this is another really important analytical technique that comes up a lot, right? So once this capacitor has undergone its little charging, right? So if we had looked at the voltage across this capacitor again, like we had drawn out before, it's charging up, and it stops. And why does it stop? It stops because the voltage across this capacitor has reached the voltage of the source, right? So up here, it's exponentially increasing to whatever voltage of the source that it sees. And by Ohm's law, we know that the current through that resistor is V over R, right? And if the voltage at this end of the resistor is Vs, and the voltage at this end of the resistor is Vs, and we take that over whatever the resistance is, that's just zero over R, right? Which is zero. So again, at some point, the capacitor, the current through this capacitor becomes zero at DC, which is why, for the sake of analysis, we can just consider this to be open circuited. And again, that's an important thing to consider when you're working through things. All right. So capacitance is additive in parallel. So this is a little bit different from resistors, right? We learned that resistors are additive in series, or resistance rather. Um, but it actually turns out that capacitors combine like resistors in parallel when they're connected in series. Right, so when you have a bunch of these capacitors connected in series like so, right, one after the other like that, then you can find the equivalent capacitance C by taking 1 over C is equal to, the sum of 1 over, all the inverted capacitances basically. And so it turns out, that in any case, whenever you have capacitors in series, the total effective capacitance will be less than, if you just had the one, right? If you pick out any given one, it's going to be less than that one. Um, And then if you have capacitors in parallel, then again, this capacitance actually is additive. You can add these up together to get the total effective capacitance there. Um, and this is important because you can't store as much energy when you have capacitors connected in series, right? You can store a lot more when they're in parallel. And you'll typically see capacitors in parallel as opposed to in series with things, especially if they're being used for energy storage. Um, and so, unless there are any questions on anything, I'm going to jump to the iPad to run through um, these examples, but feel free, at any time, feel free to shout out if you have any questions, but now especially because I'm making this transition here. All right.
I have a
Oops.
question, RJ.
Yeah, what's up, Lucas?
Um, so at the beginning of like say like t equals zero, does the capacitor kind of act as a short then?
Yeah, I mean, so that's actually a
Like
tricky
at
question. It depends
just for a
on how
minute,
much,
kind of?
it depends on, the initial condition of the capacitor, right? We can't really
Okay.
make that statement unless we know how much charge is accumulated on the capacitor.
All
And
right.
that's a really important idea, for the next chapter, actually, when we look at transient circuits, is you always need to keep in mind the initial condition in order to determine the state of things. But generally speaking, yeah, when you're making some kind of analysis like that, um, you typically start off with the assumption that the capacitor has no charge, right? So if Q is zero, which is CdV or CV, right? If there's no charge, then this
Hmm.
implies that the voltage is zero, right? So yeah, it's effectively a short, like you'd mentioned.
Thanks.
Yeah. All right. Yeah, unless there are any other questions, we'll jump to these problems. And I'm guessing you guys can see the iPad screen, but let me know if you can't. So this first question, 6.1, we're looking at charge accumulated on two parallel conductors charged to 12 volts. We know that first off, we have, these two parallel plates, got 12 volts, and it's got a charge Q of 600 picocoulombs, and it's asking what is the capacitance. So this is, straight plug and chug, right? We know that the charge, um, sorry, we know that the charge is given by CV, and so we can figure out that the capacitance is Q by V. So this is going to be 600 picocoulombs divided by 12 volts. And write that out. So if we've got 600 picocoulombs, sorry, so it's going to be 50 picofarads, right? You just take 600 divided by 12, you can keep the P, and then C over V just gives you farads there. So just straight plug and chug, it's not a particularly difficult problem there. Just wanted to illustrate that one, I guess. And so this next one is a little bit more interesting. So we're looking at 6.2, and it has a couple waveforms, which is pretty typical. When you get to analyzing these kind of things, you're always looking at the waveforms. So we're looking at the voltage as a function of time across a capacitor. And oops. And so they've drawn it out like so. At time t equals 6 milliseconds, the voltage has reached 24 volts. And then it starts to decline back down to zero, and it reaches zero at time 8 milliseconds. And so again, this is for a 5 microfarad capacitor. And we want to determine the current waveform. So how do we do this? So we're going to, recall the capacitor equation, right? I is equal to C dV by dt. And all we're going to be doing is taking the derivative of that waveform. Easy peasy, right? So fortunately, this actually is a pretty straightforward change here. So we have 24 volts over 6 um, milliseconds. So that gives you 4 volts per millisecond in this first interval there. And this is, from t between 0 and 6 milliseconds. And then on this bottom one, or on this next interval, right? So that's kind of from here to here. And on the next interval, this is a little bit more tricky because, we have a non-zero um, intercept there, but you can kind of easily find the slope. So we're going down 24 in 2 milliseconds. Um, and then, they found that intercept to be 96 milliseconds there. Um, or I guess 96 volts rather. And, I'm not gonna do that here, but I'm sure you guys can figure that out. So looking from, oops, time between 6 and 8 milliseconds there. And um, right, and so these are the equations for the voltage. And I actually forgot to put times t here. These are times t. And just to write it out more clearly, so we have basically 4t, and then we have basically minus 12t plus 96 there. And if we, well, now I'm blanking on this because they've got 20 milliamps. Oh, okay, sorry. Because we take sorry, yeah, so we take C, right? So these are the equations for voltage. And then to find the current, we take C dV by dt, which I've written up there. So if I take the derivative of my 4 there, I get 4, right? So I'm going to get 5 microfarads, basically times 4, and then also times minus 12. Um, so in the first interval, I get 20, and this is going to be in milliamps because I've got um, micro basically, and then I've got divided by milliseconds over on the other. So here, if I just write it out, if I got micro over milli, that's going to be equal to milli, right? 10 to the minus 6, 10 to the minus third. Can be 10 to the minus third. Sorry, it's kind of going all over the place for this example, but basically, so I've got 20 milliamps there, and then I've got minus 60 milliamps in the second interval. So if I were to sketch this out, I've got 20 up until t equals 6 milliseconds, and then I've got minus 60 right in my second interval there, milliamps, and then it goes back down to 0. Um, yeah, I'm sorry that was a mess, but basically all you do is you figure out equations for the voltage, and in this case it's a piecewise function, right? So we need to break it up into our two intervals, and then you take the derivative of your voltage and you multiply that by the capacitance to get your um, current waveform here, which is in milliamps. All right. Any questions on that? Yeah, that was not the greatest presentation. I apologize. And for this last example, we're just looking at the energy stored um, in the electric field of the capacitor. In the previous example at t equals 6 milliseconds. And so in order to do that, we had shown previously that the energy is 1/2 CV squared. That's, from the slides that we kind of derived that from first of all getting the power and then, taking the integral of the power to find the energy. But anyways, so in this previous example, at time t equals 6 milliseconds, we have the voltage to be 24 volts. So take 1/2 times our 5 microfarads times 24 volts. We find that this is 1440 microjoules. So a lot of these are pretty straightforward plug and chug examples, nothing too spectacular. If you know the definitions of things and how to apply a little bit of calculus to, take the derivative of things, then you should be good for that. All right, so that's all I wanted to talk about there. Um, now, oops, we'll move on to inductors here. Oh, that's not the right screen. There we go. All right. So moving on to inductors. So inductor is just a circuit element that consists of conducting wire, and this is usually, coiled about some kind of object or even just coiled around. And once you've taken some amount of physics, at Cal Poly it's Physics 3, I think, you'll kind of learn about these properties. But if you have a current conducting, a current carrying conductor, it's going to produce a magnetic field. And actually what happens when we wind, this coil around, these magnetic fields start to build on top of each other really and kind of um, create more and more um, energy storage properties, which is why we kind of can coil them around like so. Um, and so when when this magnetic field appears, it has, it actually is linearly related to the current, right? So the more current that I have going through this wire, the more magnetic field will appear. Um, but once you start to excite this structure with some amount of current, it's going to produce a voltage proportional to that rate of change of current, and it has a constant of proportionality called inductance. And so inductance is measured in henries. I've got it here as a volt second per amp. Um, and it's very complicated to talk about inductors, I think. I think people tend to have more difficulty understanding inductors because capacitors are um, a little bit easier for us to visualize, right? You just got these charges building up onto a plate, and then those charges want to repel each other, so they kind of build up this field of energy. But this magnetic field is kind of invisible to us and really hard to picture, I think. But we'll try to get through it here. Um, so again, inductors store energy in this magnetic field. Um, so as we have the current flowing through the conductor, it starts to build up a magnetic field. And then this magnetic field actually induces a voltage that opposes the change in current. So you can imagine, if I've got current going this way, there will be some back EMF, right? And it'll kind of appear in each of these little coils going that way, right? It'll try to send current the other way effectively, but right, so it's going to generate this back EMF to oppose that initial change in current, right? It's kind of, and then so we've got this back EMF, which is proportional to the rate of change in current. So V equals L di by dt. Um, and again, we go and can find the power associated with an inductor is L di squared by dt, right? Because if we have I times V and we know what V is, we can pretty easily figure that out and then figure out the energy just by taking the the integral. And so that's given by 1/2 Li squared. Um, and then, the inductor circuit symbol is just kind of a coiled wire that I've got drawn out here. Pretty straightforward. We've seen those before. Um, and so going back to the idea of these concepts of continuity, the inductor current can't change instantaneously. So we've got V is equal to L di by dt, and we can solve for change in current over time. Di by dt is V over L. And again, this kind of assumes that this derivative exists. So the current must be differentiable and can't have any jump discontinuities, and therefore this current can't change instantaneously. Um, yeah. So inductors behave like a short at DC. Um, we had looked at capacitors and kind of figured that they behave like an open, but inductors have this magnetic field trying to keep the current constant. Um, and since we have this defining equation for the inductor, we use L di by dt. When the current stops changing over time, right, we've reached a DC condition. So di by dt is 0. And by this inductor equation, when di by dt is 0, the voltage is also 0. And since the voltage is 0, we've created a short, right? There's no voltage drop across a short. Um, and again, this becomes very useful when you're actually performing analysis of, DC circuits, which actually comes up a lot. Um, and so inductance is additive in series, much like resistance, and inductors actually combine exactly like resistors. So if we have, a bunch of inductors in parallel, you can find the equivalent inductance by taking the inverse of the sum of the inverses. And then that's a typo. So for n inductors in series, you can find the equivalent inductance by just adding them all up. Um, all right, so moving on back to more example problems, unless there are any questions here, feel free to shout out again. Okie doke. So we're looking at example 6.5, and this one's actually a fun one. So we're trying to find total energy stored in this circuit. And this is going to look pretty. When I first look at this, I was a little worried because I actually wasn't completely sure how to do this. But after reading about it, I quickly figured out what they're trying to accomplish here. Um, so here's the circuit. Got a lot going on. So it's got a 9-volt source, um, 6 ohm resistor, a C1, which they have as 20 microfarad, inductor 1, which is 2 millihenries, 3 ohm resistor there, a 3 amp source here, another inductor here, which is 4 millihenries, and another capacitor, which is 50 microfarads, and then a 6 ohm resistor here. Um, and so the trick in doing this is actually to remember that the properties of these energy storage elements at DC. So we have two DC excitations here. We've got the 9 volt voltage source and the 3 amp current source. And so this is going to be a DC circuit. So we can redraw this, right? The capacitors are going to become open circuits. The inductors are going to be short circuits. And the resistors are just going to sit there and do nothing, right? And so here's a circuit that we're actually looking at. Um, and we know that the energy for a capacitor is given by 1/2 CV squared, and the energy for a inductor is given by 1/2 Li squared. So at DC, right, this is a very simple um, problem now, right? Because we just have, just resistors and these two sources here. Um, so it looks like we can start by taking KCL at this top node here. So we can find that IL2, right, if we take that to be going out, is going to be equal to IL1 plus 3. Um, and then we can also apply KVL across the entire loop out here, right? So I've applied KCL there, and then I'm going to apply KVL around the loop. And so that gives me 9 volts plus 6 IL1 plus 3 IL2 um, plus, or sorry, so these are um, minus, and then minus 6 IL2 is going to be 0, right? If I'm taking these to be the voltages across these resistors here, I'm dropping down through all of them to get back up to 9 volts. Um, so then you've got two equations, two unknowns, from these two guys here, and you can actually solve for IL1, and this will give you minus 1.2 amps. And then you can solve for IL2, and that'll give you 1.8 amps here based on what they've found. And so that gives us directly the energy stored in both of these inductors. Um, we know that the inductances for L1, so if I do the energy through L1, I'll find that my inductance is 2 millihenries. And then my current is minus 1.2 amps. I square that, and I find that the energy in inductor 1 is 1.44 millijoules. Um, right, and you can repeat that to figure out the energy in inductor 2 to be 6.48 millijoules. That's pretty straightforward there. Um, the next thing we want to do is figure out the voltages for the capacitors, right? And so that's going to be this right here. So that's VC1. This is going to be VC2. Um, and this is actually pretty easy now that we have the inductor currents because VC2 is going to be the voltage across that resistor, which is going to be IL2 times 6, right? So I'll just write it out here. We know IL2 is 1.8 amps. So if I multiply that by 6, um, Well, they've got 10.8. Maybe that's not right. What did I do here? Six times, I guess 6 times 1.8 is 10.8. That didn't make sense in my head. All right, so VC2 is 10.8 amps. And then if we look at VC1, which is um, right there, that's going to be 9, right, minus 6I2, or 6I1 rather. And so I1 is minus 1.2, right? And so that's actually going to be positive, which means that this is going to be 16.2 volts if you plug in your 1.2 there. Um, right? And then to find these powers, or sorry, these energy stored in these elements, you just take 1/2 CV squared, and this is going to be C1 in this case. Um, and these capacitors, C1 is 20 microfarad, and then the voltage across C1 is 16.2 volts. You're going to take that, square it, and you'll find that that is equal to 2.62 millijoules. You can kind of repeat this for the second capacitor and find that that's 2.92 millijoules. And if you add up, you know, this, 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 and this, then the total energy is going to be 13.46 millijoules there. Pretty, pretty straightforward, I think. So the next one that I have here is 6.6. And I just kind of wanted to point out how similar it is to the one that we did with the capacitor, right? So you have this, instead of voltage, you actually have this inductor current equation. And so that's going to be in milliamps, right? And it's going to be increasing to 20 milliamps over 2 milliseconds. And then it'll decrease down back to 0 after 4 milliseconds. And so the objective of this is to find a voltage waveform for an inductor with 10 millihenries, right, of inductance there. And so basically, again, all you would do is figure out an expression for I of t. And in this case, I'll just write it out. So they've got it here to be 20 milliamps per 2 milliseconds, right? So again, that's just going to be 10, basically 10t. Um, for t, I usually like to write it like this. From t 0 to 2 milliseconds, and then the next interval, right, this second half here is going to be minus 10t plus 40. Um, and this is for t between 2 and 4 milliseconds there, right? And you would take our inductor equation and you would figure out that the voltage, um, since our inductance is 10 millihenry, you would take the derivative of 10t is just going to be, um, or wait, yeah, the derivative of 10t is going to be 10. right? So this is going to be 10. And this is going to be in millivolts. So this is going to be 100 millivolts from t between 0 and 2 milliseconds. And then our second expression here is going to be 10 millihenries times minus 10, right? The derivative of this minus 10t plus 40 is going to be minus 10. Right? And so this is going to be minus 100 millivolts there. And this is going to be from t between 2 and 4 milliseconds. So we just kind of draw that out. And I'm just kind of continuing with this example because we've really got 5 minutes here and there's no possible way we're going to get through chapter 7 in 5 minutes. Um, anyway, so if we were to draw this out, it's going 100 millivolts for 2 seconds, and then it goes minus 100 until 4 milliseconds, and then it just flatlines there. Um, cool. So that's the last problem here I wanted to cover. Um, are there any questions on that? No. All right. So I think I think we ought to just save chapter 7 for next time, but maybe I'll just kind of run through a little bit of it here. So, the learning goals are calculating initial values for inductor currents and capacitor voltages, and then looking at the voltages and currents in first order transient circuits, and then looking at the voltages and currents in second order transient circuits. Um, and after reading this chapter, it really seems like they didn't do the chapter much justice with these learning goals because this is probably one of the more involved chapters. I'd say that having to do these first order and second order transient circuits is probably as difficult as circuit analysis gets. Um, obviously, as you get into more control theory and more advanced specialized topics, um, things will get more difficult. But as far as circuit theory is concerned, I'd say these kind of things are some of the most difficult. Um, but I think, yeah, I guess we'll just leave it for the next meeting because I'm not even going to attempt to, go through all this material right now. Um, but yeah, thanks for tuning in here, guys. I'll stop the recording here and take any